and the linear traces this way. And then, of course, it could come out the x-axis, right? So in that case, you would have y and z in here, and you wouldn't have an x. Come down this way. All right, next surface, parabolic cylinders. Parabolic cylinders, when you do the traces, you get parabolas and lines. So I'm just going to take you straight to it, and we're going to look at it. There is a parabolic cylinder. It's just a sheet of paper. It's like folded up like a parabola, all right? This is the equation of a parabolic cylinder. Again, you have two variables only, right? A third variable is free. So here y is free. You have z, and then you have some constant in front of x squared. I think we would all agree, like y equals x squared, we know that's a parabola. But if you have z equals x squared in three-dimensional space, you have this thing. Y is free, so it kind of folds down the y-axis this way. How many different versions of this could we have? Oh, I should show you the traces here. Where the heck are they? Oh, parabolic traces. There we go. So there are parabolic traces. As you cut through it with the plane this way, you can see all the parabolas. Can you all see those parabolas? And then they said it was also lines. So let me show you the linear traces. So you cut through it this way, and you can see it intersects in lines. How many different types of equations could we have? We have z equals a constant x squared, z equals a constant y squared. That would go down the x-axis, right? So here, this is z equals a constant x squared down the y-axis. Z equals a constant y squared. X is free down the x-axis. What else, though? How about x is equal to some constant times y squared? This time z is free. So now it's going to be like this. Or you could have x equals a constant times z squared. So y is free. It goes this way. Are there any more? Yeah, there's two more. You could have y is equal to constant x squared. This one's going to go up and down the z-axis because z is free. And then y is equal to constant z squared down the x-axis. So there's 6 different versions of parabolic cylinders that we can see. All right, moving along. Ellipsoids. All traces are ellipses. Can you visualize that? It's just an egg, right? It's just an egg, basically. We have, you either hit it in the ellipse like that, or if you cut it another way. Oh, I'm moving the wrong one. Man, this thing's slow. I went too far. There. Can you all see that on the other side? Hits like an ellipse. So I can get these out of here. I can just show you all the traces. So there's traces that way. Here's traces this way and that way. So that's cutting it with the 3 different planes. This way, or that way. And you can see all those traces are ellipses. And what does the equation look like? So notice this is the first time we've seen this. What? All 3 variables are here, right? All 3 variables appear. Not only are they all here, they're all squared, and they equal 1. This looks like an ellipse in 2-dimensional space, right? If we take this piece out, that's an ellipse in 2-dimensional space. We're adding that, and now we have an ellipsoid, 3-dimensional egg. And there's no way to vary this. There's not like 6 different versions of this like the previous one. An ellipsoid's an ellipsoid. 3-dimensional space. Now, if you change A, B, and C, it's going to make it maybe wider than it is tall or deeper than it is long. But otherwise, there's only one equation. All variables, all of them squared, equals 1. Next shape. I'm going to give you a sheet that summarizes all this, all right? I left it on the copy machine before I came into class, so I'll have to go get it on our break. Next one, elliptic paraboloid. So traces are ellipses and parabolas. There you go. That's it right there. It's kind of like a bowl, right? It's a parabolic bowl. So if I start cutting through it this way, like that, what are those? Look at it from the top. What are those? Ellipses. So those traces are ellipses. And then if I cut it through with YZ plane, so I'm cutting it like this, what are those? Parabolas. And if I cut it through with the XZ plane, which is cutting it like this, you can see parabolas. So in one direction it's ellipses, in two directions it's parabolas. What does the equation of one of these look like? So all the variables are there again, right? All the variables are there, but only two of them are squared, and one of them is not squared. That's how you know you're looking at an elliptic paraboloid. Now, when you look at this elliptic paraboloid, would you all say that this, would you all agree that this looks like it opens like up the z-axis? Would you all agree with that? Okay, then notice that the z here is the only one that's not squared. That's what determines which axis you're opening on. So there are other versions of this. Like what if this was x squared over a squared plus y, z squared over b squared equals y over c? Then that would go down the y-axis like that. So come out this way. And then we could have it come out the x-axis, same way. Like that. So do y'all see how the equation changes? I told you this is a tough section. It's not a lot other than just trying to understand the patterns. Next one. There's only 13 more, so hang tight. No, we're almost done. Hold on. Hyperbolic paraboloid. Traces are hyperbolas and parabolas. This is going to be a weird looking shape. There it is. Let's look at the equation first. Doesn't the equation look a lot like the previous one? Two of the variables are squared equals one of the variables not. What's the big difference? There's a minus sign in between those two variables. And that minus sign, just like with hyperbolas, this is going to have an effect here. So that's a weird looking shape, isn't it? It's a weird looking shape. One of the questions we're going to be able to answer pretty soon, not far from now, is if I were to imagine this surface as a real physical surface, all right, and I were to take a, let's say a ball, and I were to put it on that surface, we will be able to determine exactly the direction at which it will roll. Okay, so like what direction that ball would roll. But first, before we can do any of that, we need to just be able to like recognize a surface. All right, so there's the equation of that surface. And this one's kind of tough because you can't really say like what axis opens up or, right? It's kind of weird. So let's just look at the other versions. So here's the other version. That one's kind of opening out the y-axis because the y is on this side. And then we can have coming out the x-axis kind of towards us like this, and there the x is by itself on that side. Oh, I never showed you the traces, did I? I'll convince you, hopefully, that you have. If we cut it with the ground and look at it from the top, what are those? Hyperbolas. If we cut it this way, on the side, what are those? Oh, I think I hit it again. Hold on. Yeah, there, I didn't do it. There from the side. Look at it that way. What are those? Parabolas. And then this way would also be parabolas. Okay? So can you imagine trying to graph that by hand? Like you start fixing constant and then starting to draw all these parabolas? What a pain in the butt that would be. All right. The two different other ways. And then now, oh, a cone. Okay, so cones. Cones are nice. Here's the equation of a cone. They're all there. They're all squared except one of them's on the other side. So when you see something like this, it's going to draw a cone. And the The traces are circles. What are those? Hyperbolas, because you have like a top and bottom, like that. And then the other way would also be hyperbolas. So cones. And then of course they could go out the other directions also. Two more. Hyperboloid of one sheet. What does that look like to you? Does that look like something you've seen before? Nuclear reactor, silo. They use that shape on purpose. It has to do with the heating and the way things cool off. They use the shape. So this is the equation. Man, that looks a lot like what? What equation does that look a lot like? Except, like if this were a plus, what's this? What is this? An ellipsoid. That's an egg if it's a plus there, right? But because that's a minus right there, you get that. And this one, I think we would all agree, kind of opens up the z-axis. And the way you can remember that is the z is the one that's negative. So if I switch these around, then I can make this thing come out the different axes. So like if I put the negative on the y squared term, then it'll go out like this. And then if I do it on the x squared term, it'll come out towards us. Should we look at traces? What are those? Those are hyperbolas, right? And then this, hyperbolas again. And this, let's see, ellipse. So we have hyperbolas and ellipses are our traces here. Last one, a hyperboloid. Oh wait, I forgot to go that last direction. Sorry, out the x-axis. Okay, hyperboloid of two sheets. This is basically like that shape we just had. If you kind of pull it apart and it stretches, and then like the middle piece kind of separates and comes together. Does that make sense? Stretch it and then they bowl out together. So here's your equation. So what's the difference in the equation? Two of them are negative, only one of them is positive. And the one that's positive is the one that it kind of opens up and down that axis. I don't expect that you memorize every single one of these. You just need to be able to, if you see it, reference something so that you know what it looks like, all right? And I'll give you a handout for that. All right, so that's your hyperboloid two sheets. You can go both ways. All right, now before we do this, I just want to remind you that, okay, so you tell me what this would be. So what is that? That's an egg, right? That's an egg, right? And where is that egg centered?
It's centered at 2, 3, 1, or 2.
Those have to do with like the widths and heights and depths. I'm saying where would the center of this egg be? The origin, right? So what if I want to take that egg and shift it? Let's say I want to move it around. Then I would do this. So this is the equation of an ellipsoid that has been shifted. So all the shifts that we've had in the past, they can be translated over into this now. All right? So just like we had the sphere had the center HKL, this is an ellipsoid. We notice it because it's variable squared over constant squared plus variable squared over constant squared plus, so all positives, all squared, they all appear here, equals 1. We know it's an ellipsoid. The HKL is just going to be where it's centered, all right? So that would extend to every single surface I just showed you. The HKL would just be shifting, where it shifted, all right? So now what I'm going to do is we're going to do an example where I'm going to give you the equation and you have to identify what it is, all right? there it is. So all I want us to do is to classify this, identify what it is. So when you look at it like this, can you get it into one of those forms? What's our time? 3:18. Let's do this. Let's take our 10-minute break right now. Is that all right with you all? Let's do it right now. I'm going to go down to the copier and grab those things I printed for you. And then we'll continue with this when we get back. And you'll have the handout, so it'll help you get through this. All right? should be 5 there. You want to keep one for your friend there? Yeah. All right, so this is a summary of the different shapes. It doesn't have a sphere on here, but so on this first one here, we're asked to identify what this is. So when I look at this, I'm like, okay, I've got all 3 variables squared, right? So it could be an ellipsoid. It's not an elliptic paraboloid, right? It's not a hyperbolic paraboloid, right? Because those don't have all 3 squared. Here, one of the variables on one side, 2 of the variables are on the other, and there's addition. So what does this look like? It could be here. What's that? A cone, right? A cone. But it needs to look like this form. So I could rewrite this as x squared over 1 squared equals y squared over what squared?
It would be,
So how could you rewrite a 2 in the numerator as something in the denominator?
it would be 1/2 squared.
Yeah, couldn't I do like 1/2 down here? Like that's the same as a 2 up here, right?
Yes.
But I need that to look like something squared. So what if I do the square root of that squared? So that would be the constant that's being squared underneath the y, and then here we'll do the same thing. Z squared over 1 over 3 square root, but then that squared. So there you go. There's your cone. All right, what about, let's look at another one. Okay, how about this one? By the way, this cone that we just looked at, what direction would this cone be opening?
It would be opening along the x-axis.
Yeah, it'd be coming out like towards us, like out on the x-axis. All right, how about this one? 2 of the variables are squared, one of them is not, right? 2 of the variables are squared, one of them is not. So that eliminates quite a few of these already, right? Elliptic paraboloid or hyperbolic paraboloid? Yeah, we have to get it to look like this. So let's get our variable that's not squared by itself on one side of the equation, and then the other side we'll move those over, which changes our y squared to positive, and our z squared term will become negative. So that's that, right? So this is looking like a hyperbolic paraboloid, right?
Yeah.
We just need to make it look like this form. So I could rewrite this as x over 1/4, but then square root, and then squared, right? Oh, wait. Oh, sorry. It's just, yeah, sorry. I'm thinking of those. So x over 1/4, that would be like our z over c in the formula. And then over here, y squared over 1 squared, then minus, now this one's like the previous one, z squared over the square root of 1/3 squared. Okay, so it's a hyperbolic paraboloid. Is this pretty straightforward? Okay. Let's see, I should have at least one more. Yeah, this one right here. This one's a little bit messy. Any thoughts here? So you have all 3 variables are there and they're all squared, right? But then you also have all the other x, y, and z all linear. So that none of these look like that, right? None of these look like that. So any ideas on what we're going to have to do? We're going to group them by variable, and then what? Complete the square. Yep. So I'm just rearranging by variable here. And let's see if we can complete the square quickly here. So if I complete the square on those two, I'm going to take half of that and square it, right? So that's going to be negative 1. I square it to get 1. So I'm going to add and subtract 1 next to this. So x squared minus 2x. I'm going to add 1, subtract 1. Okay, so that's completing the square on that one. This one, you have to be really careful, right? Because of that minus sign right there. So I'm going to do that one over here. So to complete the square on that, I first need a coefficient here of 1. So I'm going to factor negative out, right? Then complete the square on this. So I'm going to take that, I'm going to take half of it, square it, add it, subtract it. So this will be a negative. Then I'll have y squared minus 2y plus 1 minus 1 inside the parentheses. And then I'll keep going. So this is minus, and then I'm going to have y minus 1, that quantity squared. Those are those three right there. And I still have minus 1, close parentheses. And then I'll go ahead and distribute the negative back through. So this is going to become, this right here will become minus the quantity y minus 1 squared. That's the negative to here. Then the negative and negative will become plus 1. Okay. I didn't break this one down. I'll have to do it on the next line. This one I don't have to worry about that 1 in front, right? It's already positive 1. So I take half of 4, square it, add it, subtract it. So I should get z squared plus 4z, add, subtract 4. And then I still have the plus 2. Like that. And now I'll just finish the completing of the square on this one and this one right there. So we've got x minus 1, that quantity squared. That's these three. Minus 1 minus y minus 1 squared plus 1. And then plus z plus 2 squared minus 4 plus 2 equals 0. And if I put all my constants together, what will I have here? I'll just get a negative 2 on this side, right? And why don't I move it to the other side? Okay, there's where we are. Almost a sphere, almost, right? Except for this. I needed to be a plus to be a sphere. So it's not a sphere. I have all three variables squared. Now, the thing to notice here is that this is something that's been shifted. Okay, so we've got like an HKL here. We've been moved around. We're not at the origin anymore. But what is it? Hyperboloid of one sheet. So that means we have two of the variables that are squared that are both positive and one of them that's negative, but we need it to be equal to 1, right? So we have to divide everything by 2 to do that. So let me divide this by 2, divide that by 2, divide that by 2, that becomes 1. And so remember, this is like, this is actually square root of 2 squared, square root of 2 squared, square root of 2 squared. So hyperboloid of one sheet. We could rearrange it too if we wanted. We could put the negative 1 right here and move that positive 1, but I think we're good at this point. Okay?
And then negative y just means it's opening the y-axis, right? That's what determines which way it opens?
Yes, so the one that's negative is going to give you the axis. So this is actually like kind of left and right instead of up and down or out and in. So it's like something like that, if this is our y-axis. All right. That's it. I think that's it in terms of examples for this. The most important thing that I want you to be able to do here is what we just did right there. Give you something, complete the square, and then determine what it is. So there you go for homework. All right, finally, we have made it to 10-7. So it's taken us 7 sections to get to a place where we can start doing some calculus. So we're going to talk now about vector functions and space curves. Now we already have defined a vector function. The vector function we've already looked at here, I'm going to put on the side over here, was that couch potato thing. This function, r of t, was a vector-valued function. It takes in a number t and it spits out vectors, right? Takes in a number, spits out a vector. So now we're going to get more general and talk about general vector functions and space curves. So any function, all right, any function written r of t equals, and then two components. So this is a two-dimensional vector where the first component is some function of t and the second function is second component is some function of t. Or in three-dimensional space, some vector function where you have three component functions, f, g, and h. This is called a vector function or a vector-valued function. So the important thing, I guess, to note is that these things inside here are just real valued functions, functions that you dealt with your whole life. Also important is to understand that the domain of a vector-valued function is a number. So a number goes in, then a vector is going to come out, and that vector is either going to be two-dimensional or three-dimensional. These functions are called component functions. That's just language. Okay, so we call this the first component, second component, right? First, second, and third. The graph of a vector-valued function, either in two or three-dimensional space, is going to be a curve. Right? Now, when we use the word curve, we can use that very loosely because a straight line is actually going to be considered a curve to us. All right? But it doesn't have to be straight anymore. Now it can actually do something, it can kind of wiggle around. So all vector-valued functions are going to give you some sort of curve in either two or three-dimensional space. They do not draw surfaces. They only draw curves. So here's your first example of a vector-valued function or a vector function. It is the function r of t equals, first component function is t squared, the second component function is 1 minus t cubed. So if we start plugging in values of t, and in this case, I'm just going to restrict our domain to only positive numbers. When we plug in 0, we get a vector, right? We plug in 1, we get a vector. 2. When we plug in all these numbers, we get vectors. Well, here's a picture of what it is. All right? So if I start plugging in values of t, right now, if t is 0, it draws me that red vector, which takes me to that point. If I plug in another value of t, it's going to take me to a different point. And you can almost look at it like a clock playing in the background. If I start the time and then start moving, here's what it does. All right? So it draws me this blue curve. Now, it continues to go on forever down here, but I have to at some point stop. All right? So it's just a space curve. All right? It's a curve in space. In this particular case, two-dimensional space. Here's a three-dimensional vector-valued function. And I want us to think, hold on, my keys are holding my microphone, pulling it down. Okay, there we go. All right, so look at this one. The first component is cosine t, second component is sine t, third component is t over 5, and we're in three-dimensional space. So let's see how many of us feel comfortable with just these first two components. Do you all know what that would draw just in two-dimensional space? If this wasn't here, if I let t start going from 0 and getting bigger, what would that draw?
Like a blue line?
Let's draw it. Let's actually do it. We'll come back to this in a second. R of t, cosine t, sine t. And you might want to put a little asterisk next to this because this thing we're going to use it a lot. Okay? This right here. It'd be a circle. That's right. In two-dimensional space, let's see what happens. let's just, it's almost like we could do a t table. Here's t, here's r of t. So what would happen if we start at t equals 0? Where would we be? So cosine of 0 is 1, and sine of 0 is 0. So we would be at the vector 1, 0. So this is x, this is y. We would be 1, 0. We'd be here, wouldn't we? And there would be a vector. But it takes us to that point. And then let's pick another value of t. Now, because these are trig functions, I'm going to use some values that we're familiar with, like pi over 4. So sine of pi over 4, or sorry, cosine of pi over 4 would be root 2 over 2. And then same with sine. And that would take us like here, right? That's not that great there. And you can imagine that if you kept on doing this, right, kept on plugging in bigger values of t, you would eventually start drawing the entire circle, right? And then what would happen once you get back to 2 pi and keep going with t? It would just keep on drawing circles, wouldn't it? Just keep drawing circles. So I have a very, very profound question to ask you. When you look at this thing right here, that is a circle, right?
Yes.
That's that circle, isn't it?
Yes.
Okay, kind of. Back in college algebra and pre-calculus in Cal 1 and Cal 2, when we look at this, we would say that this curve is not a function of x. Why is it not a function of x? It fails the vertical line test, right? It hits at 2 places. We all know the vertical line test, right? Now, I want you to understand what's happening here. What's happening is this. Over here, if I plug in a value of x, it's going to spit out 2 y's. For example, if I plug in x is 1/2. So if we look at a t table, here's x, here's y. If I plug in 1/2, what is my y value going to be? Well, let's see. We plug in 1/2. 1/2 squared is a fourth, plus y squared must equal 1. Let's solve that for y, right? So that would be y squared equals 3/4. And then to get y, you would have to do plus or minus, right, when you take the square root. So what you have is an input, right? 1 input and 2 outputs. Functions don't do that, right? Functions are 1 input, 1 output. Yes? 1 input, 2 outputs, not a function of x. That's the way we did look at it, right? Now come over here. Is this a function of t?
Yes.
Yes. Because you never have a problem of 1 input going to 2 outputs. Look, if you try and say, look at this point, right? Like those 2 points like over there. This point came from a t value, pi over 4, right? This one comes from a different t value, right? And even when I go all the way around and come back to this point, I'm on top of it again, aren't I? But that's coming from a different t value. So I can draw a circle on top of itself infinitely many times, and it still is a function of t. And this is critically important in what we're trying to do, because we're very limited when we draw things in two-dimensional space using the idea of y as a function of x. When we do our calculus, if our calculus depends on this, we are limited in what we can actually do calculus with. We can't do this. Now, we can cut off the top and work with just the top, but we can't do things that are more dynamic, I guess, right? Like in the real world, you want to have an object that is allowed to move around freely and be able to talk about slopes of tangent lines and things like that. You don't want to say, okay, yes, we can do the calculus as long as it passes a vertical line test, because then you're very restricted. Make sense? So this idea of a vector function is going to allow us to draw complicated curves in two-dimensional space or three-dimensional space, and we are going to throw the vertical line test out the window, not have to worry about it. That make sense? Okay, so that's an important thing that's happening here. Okay, so cosine t sine t will draw a circle. And just a circle on top of a circle just keeps on going. So what happens if I do that here? I start drawing circles in the x and y components of the curve, but my z component is just linear. So now you're trying to draw these circles, right? In the xy plane, you're trying to draw circles, but your z is doing what? It's growing linearly. So what are you going to draw? It's going to be I heard a couple of things, but this is it right here. It's like a spring. Okay, so if we look at it from the top, you can see that we maintain the radius the whole way, right? The only thing that's growing is the z coordinate of the points keeps rising linearly. All right? So as we kind of start the clock here, we start varying our time, we start going up this spring, right? And so something we might want to know is like, I don't know, right there, hold on, let me just stop it. Right there, if I were to imagine this is like a rocket or something, right? It's like out of control. And imagine at that instant in time, we shut off the rocket's engine, right? Then the question would be, what would the direction and speed of that object be at that point, right? So it's kind of like if you're swinging something on a rope, and then you cut the rope, where's it going to go, right? It's going to go in a path that's kind of like tangent to, yeah. That's what we're going to ask, okay? Or we might ask ourselves, see this path? How long is that path? What's the length of that curve? If we were able to cut it off the page and stretch it out, what would be that arc length? So it's some I guess valid questions that we'll be able to ask. All right, so just like we did in calculus, we went through a progression in calculus, right? Cal 1. We started out in Cal 1, we say, hey, everyone, welcome to the idea of the limit, right? From the limit, you develop an idea of continuity. And then from continuity, you start taking derivatives, right? And then you do integration. So we're kind of going to do the same thing here. We're going to say, okay, if we have a vector valued function as drawing these things in 2 or 3 dimensional space, first of all, what's the limit of one of those functions? And I've got really good news for you. If you want to know the limit of a vector valued function, whether or not it's 2 or 3 dimensional, all you have to do, so you're saying like, what's the limit as t approaches some value a of our vector valued function? All you have to do is take the limit of each component function separately. So it works very nicely. You just look at each component, take the limit in each one. If the limit exists, then you have an answer. 3-dimensional space, you take the limit in each component function, and you're done. So I have an example here. So let's find the limit as t goes to 0 for this vector valued function. So let's first take a note of something. What is r of 0? So if I plug 0 into this vector valued function, what does it spit out? Well, you can't plug 0 in, right? You can't. This is undefined, right? This is undefined. If I ask you to plug 0 into that, that's like me giving you this right here. And I ask you to figure out what f of 0 is, right? You can't plug it in, right? Can't have division by 0. So we can't plug 0 into this, but that's not the question. The question is, what is the limit as t is approaching 0, right? So if we ask what's the limit as t approaches 0 of this vector valued function, then what we want to do is take the limit as t approaches 0 for each of the component functions. Cosine t, limit t approaches 0 of sine t over t, and then limit as t approaches 0 of e to the t minus 1 over t. And our answer is going to be a vector, isn't it? Okay, so let's take these one at a time. What is the limit as t approaches 0 of cosine of t? That's just 1, because there is no problem there, right? So anytime we take limits, we always just want to try first doing an evaluation. Can you plug 0 in? See what you get. So here, 0 cosine 0 is 1, no problem. So we know that the first component is 1. Now, what about the second component? If you try and just plug in 0, you get sine of 0, which is 0 over 0, so you have 0 over 0. That's an indeterminate form, right? And what is that? So how do you deal with the indeterminate form here? It's all going to matter, it's all going to depend on you and your background at this point. I heard L'Hopital, right? So you could use L'Hopital's rule here. This is also one of the first limits that you ever learn in Cal 1. And a lot of times when you first learn it, they just tell you to memorize it. No? Is this not the first limit you ever, not first limit, but the first one that you couldn't solve algebraically? Either way, you either learned that that's 1 and you've just remembered that that's 1, or you apply L'Hopital's rule. I'm going to apply L'Hopital's rule, just because we need to make sure we know how to do that, right? So when I apply L'Hopital's rule says that I can do the same limit, but I'm just going to take derivative of the top and bottom, right? So derivative of the top is cosine t, and derivative of the bottom is 1. And now we can run that limit, and that's going to give us 1 once we do it, right? Okay, what about this one? Do we have a problem here? Do we get something indeterminate? So as t goes to 0, e to the 0 is 1. 1 minus 1 is 0. So we get 0 on top and 0 on the bottom. So again, L'Hopital, right? So what is the derivative of the top? E to the t, and derivative of the bottom is 1. Okay. Now we just hope that we can figure those out. So we have 1, and then we just said that one's going to be 1 also, right? And then this one right here is going to be, let's see, e to the 0 is 1, so 1 again, right? 1, 1, 1. So that means that if you were to draw this, okay, if you were to draw this three-dimensional curve, whatever it is, as you got close to t being 0, you would have a hole in your curve. Just like you, almost like you have a hole in a graph. There would be a hole there, but as you came in, the vector would be approaching the vector 1, 1, 1. Right? If you could actually ever be 0, that's what it would be approaching. The closer you get to 0, the closer you get to that vector.
And it doesn't matter whether you're coming from the negative or the positive.
I'm glad you're asking that question. The question is, does it matter which side? So remember with x, there's really two sides, right? Because x is a real number. So you're imagining x on a number line, and you're coming in from both sides, right? You have to look at left-hand, right-hand limit. When we use L'Hopital's rule right here, t is also a real number. And so we are actually coming in from both sides here. The only time we would be concerned is if when we did our limit, we had something like the numerator is going to, let's say, like 4, a fixed number, and the denominator is headed to 0. So what you get is something that blows up and becomes infinite. Then you have to concern yourself with, is it becoming infinite positive or infinite negative? So that would be the indeterminate form would dictate whether or not you have to worry about left or right-hand side. Does that make sense? You sure?
So when the indeterminate form is a constant over 0, like it's being to infinity,
Uh-huh.
or infinity to the 1.
Okay.
Right.
Well, infinity to the 1, it would always depend on what you would have to be looking at the actual thing for me to be able to. I can tell you this. If it's something fixed on top, other than 0, over something that's becoming infinitesimally small, 0, then I need to know which side I'm coming in so I can tell you whether or not it's going to be positive or negative ratio. If you have something like infinity to the 1, then there's many different ways that could happen, so I'd have to actually look at a specific example to be able to tell you what's going to happen. You satisfied? Sure? Okay. I believe on one of the mini exams there's a problem like this, but these limits are much more challenging. I'm basically going to be testing how far back you can go into Cal 1 and pull out the different methods for calculating limits. So there's different ways, like you mentioned, you may have something that looks like this, where you have something that's like the base is becoming infinite and then the exponent's headed towards 0. And then like what happens here, right? Like how do you deal with an indeterminate form like this? This is a rhetorical question, right? That you need to ask yourself this, and on that take-home exam, you'll have to maybe go back and do a little research through your notes to remember how to do that. I'll give you a hint that you could bring in natural log and things like that and make it work. All right, so I try and treat this class like it's the last calculus, right, in the sequence, right? So I try and treat this like where I try and bring all these things back from, I mean, I try, like on the mini exams, I try and make you go pull things from college algebra, from pre-cal, from Cal 1, just kind of like stir it all back up again. Just so, because it's the last one, so let's pull all these things together now, all right? So we can do limits of vector valued functions. There's nothing new other than the fact that if you have a three-dimensional vector,